So good morning, everyone. Yeah, so for today, we're gonna try to do DistilBERT, okay? A distill version of BERT, smaller, faster, cheaper, and lighter. Before we try to understand what is the things that they do in the coding part, we go to paper first. What is the thing that they try to do? Yeah, they propose a thing that they use a P10, a smaller one, which is called DistilBERT, okay? And they say that if they try to fine tune, they can keep good performance on par with the larger one. But the basic things that they do is just they try to use knowledge distillation during the pre-train phase, okay? And they say that after they try to distill, the size of the model reduced by 40%. Yeah, we're gonna check this one as well. Is it true or not that model has reduced to be only 60% remaining? And yeah. And another one is the losses that they try to combine, okay? Yeah, they have a language modeling, and they add two more is distillation and cosine distance loss, okay? So yeah, we're gonna try implement three these losses as well, but I'll add something more, okay? Or I'll add something more. So before we go that one, we look at the losses first. What is the thing that they try to do? Yeah, let's say because this is the distillation, they have to have a model that come from the larger one, which is we call a teacher, and the compact one, yeah, we call a student. And yeah, for today, we just do only the classification models, quite easy. Like we have a goal label, okay, we have a goal label, but yeah, but when we try to train with the distillation lot, okay, for the distillation lot, we does not use the label yet. We just use a soft target probability of the teacher, okay, and we use the student as well, okay. We use the student as well, and we compare this one with the softmax, okay. So in this case, we have a soft target between the teacher and student, and we matching with the softmax. But for my case, for today, we try to I'm gonna try to use the KL divergent loss instead. It's like it just compare the softmax probability for the both distribution and compare like student have to behave as a teacher, okay. And yeah, and another one is just cosine emitting loss. Yeah, in this one is so easy, like they have y into the weight into the PyTorch as well. Okay, so yeah, this one they just said we retain alignments direction of the student and the teacher in the hidden state vector. Okay. Okay, what is the idea of the student architecture? They say that the token embedding and the polar are removed, but the number of the layer should be reduced by 2. Okay, this is the idea. Okay, what else? So that's okay. So and the final part, you can see that they say that if the DistilBERT, this is only 60% of the model of the BERT model, and the layer that they have is by half. But you can see after they try to train, yeah, for today just use in LI. You can see that BERT based 12 layer they have 80%, is 86%, but DistilBERT they have 82%. This is quite okay. Like they just difference only 4%, but the speed and the parameter that they have is quite small and faster. Okay. So let's get back to DistilBERT. Yeah. So before then that, let me check something. Okay. So yeah, just check. Yeah, I just put this one and check the version of the each thing that I have first. So yeah, data set I used top 2.16 and transformer version is 4362. Okay, and torch version is 113. Yeah, I just check the CUDA first. Okay, for this case, I has blocked with the CUDA visible device, just only use number one because I use puffer. Okay, and yeah, as I said, oh, this one is spelling wrong. yeah, I want to use MNLI, okay, for data set. And yeah, we just download this one from the Huggingface, okay. We just use the dataset library and load dataset and just use Goo dataset, okay, and you just put a task that you want. But in this case, I try to reproduce from the Goo dataset GitHub that they provide. We can have like key name of the task, and this is the feature that they have. So you can see that after I call this one, we can have many data set inside like the 10 validation mismatch and match, okay. And yeah, in this case, we use MNLI. So they have a premise and a hypothesis. Yeah, they have a premise and a hypothesis inside. Okay. Yeah, I don't want to use SNLI anymore. I remove this. So next, so I just call the dataset 10 first, because I want to know that how many feature that dataset this one have. Okay, I just put 10 and call for feature label in this one and check a name that they have. And yeah, so you can see that I try to matching them into the dictionary as well, into the label and to ID. So they have this one, and I have swap ID to label as well, because both of this we're gonna put into the model. And yeah, we can see that they have three number of labels. So I just put into the NumPy and check a site that they have. So they provide only 3. And yeah, so yeah, I just call the model BERT, the BERT based on case, okay. But for today, we're gonna do a downstream task, which is sequential classification, okay. So we just put label to ID to label, num label inside this, okay. And I call this as the teacher model first, okay, because this is the default model. So you can see that after I call the teacher model, they have 2 layers. So you can see this is 0, 1, 2 until 11. Yeah, they have 2 layers inside. But yeah, we're gonna try to distill, but before than that, yeah, I try to pre-processing first. I want to use the mapping function from the data set. So I have to set the sentence that I have. So you can see that inside of this data set, they have a premise and a hypothesis. So I have set into the task key dictionary as well. So I just come back in this one and put task name, which is MNLI. And yeah, they just call this one because they have 2 key number 1 and key number 2, and this one is just set a maximum length 128 and maximum with them. Yeah, so now we can have input IDs, token IDs, and marks, attention marks, okay. But the things that we have to remove is the default feature, okay, which is premise, hypothesis, and yeah, and IDs as well. But initially the label, it should change from the label to labels, okay, because the model Huggingface, they require S inside. Okay, so just remove and change the name and set the format to be torch, okay, because we're gonna use the PyTorch. So then now we have this. So you can, so maybe let me run a bit, like, oh, it's quite take a long time of it. Yeah, it's 30 seconds. Okay, during they do, yeah, because I wanna let you see like what is the thing that they has tokenized already. Okay, matching all of them. Okay, now, yeah, let's say we just check what is the things that tokenize had to do. I go to the train and check the first one, and this is IDS. You can see that this is the tokenizer that they do, and yeah. So let's say if I decode back, this is the result. Okay, but you can see that for this one, they does not padding yet. Okay, so I have to padding in this one as well, because we doesn't know that what is the maximum sentence that they have. So in this case, I use the data collector with the padding instead, okay? And then just put a tokenizer from the BERT inside. And then, yeah, I don't want to use all of the things that they contain into the sample. So I just set the 10 only 100,000 and eval and test is only 1,000, okay? And then batch size that I had set is just 32. And then, yeah, we just put a padding collector inside this one. So then they're gonna patch for us. So if I see this one, if I check, this is shape only 28, right? But after we put this one, college padding, and then we check the training loader inside, you can see that the shape from this one to 28, yeah, the maximum that they have is 78. Okay, yeah, they try to padding for us. Okay, so let's get to the main part of this lecture. So we have a teacher and a student, and yeah, the student have to get a half of the layer. Yeah, okay. And to initialize things that yeah, we have to have a new model first. Okay, and then we just copy some weight from the teacher inside. Okay, but in order to do that one, you have to understand how we're gonna accept the weight. Okay, so I just call the teacher model again and check the config that they have. Okay, so you can see that this is the BERT config that they have. They have number hidden layers about 12, but I want only 2. No, I want only 6. Okay, so the things that I want to do is I have to call the teacher, call the config again. Okay, and then I just set that it's have to change to be dictionary. Okay, so let me show slowly to get more understanding. So you can see that yeah, so now it just change this one to be dictionary. Okay, and the things that I want just only the number hidden layer. Okay, so I say that this key they have to change itself from the 6 from the 12 to be 6. Yeah, to be 6. And then I just call BERT config again. Yeah, because this is the BERT config. Okay, and say that you have to change the things that they have. Okay, from the 12 to 6 and put in this one. So now we have a config from the 6 layer again. And then, yeah, I just call this one a type teacher and then put config. So this one is gonna matching the teacher with the new configuration. You can see that for now, the teacher that we have here, they was set to be a student, and the layer that they have, this is number 1, and the last one is number 5. Okay, so now we have only the 6 layer instead for now. But in this case, they does not initialize yet. Okay, so it's like we just change the number of the hidden layer, but the hidden layer that they have, they was randomized. Okay, so the things that we have to do, we have to copy every weight inside to the student. But yeah, the layer that we have from the teacher is just 12, but the student is 6, so we cannot put every layer that we have. Okay, so my case, so the things that I want to do is just only the event layer. Okay, so I want to only event layer. And but the things like if anything else is not a layer, just copy everything. Maybe it can be like an emitting bird, or even like a puller, a dot mask, or even the classifier. Yeah, this thing we're gonna copy, but the layer that they have, we just want only half or even value of them. So yeah, I set some function over here. It's like distribute the weight of the bird. Okay, so they said that either part of the entire model, yeah, we have to unpack an iterative of them. But if inside of them is the BERT encoder, which is the layer of the each one, I just want student of the teacher and the student of the student in actually just layer of each one. And I say that we have to loop. Okay, loop all of the student layer. Okay, and let the student layer for the each one load and copy the teacher instead. But you can see that index that I put is the number 2 because I said that they want only the even layer. Okay, so now we can have all of the layer, but it's an even number. Okay, but if anything does not a layer, just let me like head, dub out, or even embedding, yeah, they just load everything from the teacher to here. Yeah, that's it. Now we have a student. So you can see that if I check the parameter inside, let's say I have teacher, which is come from the BERT on the top. And the second one is the model for the student, that we have this tail. So you can see that this is like, how is it, 100 million, okay, I guess. And this is only 60 million around, okay. So if I divided them and check, oh, you can see this is 60%. So this is the things that model, the paper has claimed that it have a less parameter than the BERT-based kits. Okay, and next, what I have to do, I have to provide a loss. Okay, loss of them. Yeah, the first one is submax. Submax is nothing like just the thing that the student have to predict. Okay, and the second one is the things that they do about it sub target from the student and teacher, but I had changed to be the KL lot instead. Okay, because I want to implement and show like how does KL lots work. Okay, and the last one is just cosine embedding that they provide, and we just combine everything. Okay, and yeah, so this is the thing that I try to show. This is the KL loss. Okay, which is we have to have the output from the student and output from the teacher. Okay, and then you just map that for the teacher, you just put into the submap, which is come from this equation. You just put into the submap. Okay, but for the student, you just put into the submap and then you put a log. Okay, and then you just put 2 of this into the main losses, which is KD. And for this case, I use a batch mean. Okay, I use a batch mean. And yeah, you can set the temperature whatever you want. But for the default, I set to be only the number 1. So now, yeah, I just map this class to criterions division. And another one is just, yeah, and then cosine embedding loss. This is easy. It's like just call the function. Yeah, I set the optimizer, but I set for the student model. Yeah, and then we set to the GPU. Yeah, put both of them to the GPU and set the learning like the warm up. And another one, yeah, if you does not install this one, just install this one. What does this one mean? Okay, this one is just a metric. Okay, so then if you want to do like classification, you have to set and check the accuracy. Right? You can use this metric. Okay, so then you don't have to do something like argmax number 1. You can use this one easily. Okay, now we go to training. So yeah, you just make each batch for the training loader and then put the batch into the model. So then we can get the output. But this is the output from the student. Still, maybe I'll try over here to make more understand. Okay, this is the student output. Okay. Okay, this is student output. And yeah, you also have to do output from the teacher as well, which is called the teacher. But we have to know get, okay, because we don't want to learn anything from the teacher. And yeah, I just check that that side of the both of them is the same logic or not. I mean this logic side. Okay, and yeah, we have a classification loss, distribution loss, and the cosine loss. Okay, so just combine both of them and divide it by t. Okay, because I want to balance 3 of them. And yeah, in this case, just wanna add a loss because I want to plot something. Yeah. And yeah, for the eval, yeah, you just use the metric that you have and that's a batch that you have. Okay, you just check the prediction that you have with the argmax and the batch label that you have. Okay, and then just check each loop. So you can see that my hash trained with the 1000 is take like around 2 hours, almost 2 hours, and get this one. The final product is 76%. Okay, maybe we can check a lot first. Okay, so you can see yeah, classification lot and the main loss try to improve. Okay, try to improve a lot. And what else? Yeah, the quality divergence. I think this one quite huge. Maybe it's like student have to against with the teacher to improve, but it does not improve much. So that's why they does not keep increasing down. And yeah, cosine similarity. I think this one is like it's quite stable. So maybe they can say that both of the things that teacher and the student try to train is almost similarity already. That's why both of them get no all of the each epoch they get almost similar to the zero. But yeah, but the loss from the validation loss does not improve much. Like it's almost deadline, but yeah, at least it can improve. But initially we should check into the yeah, initially I check already like what is the accuracy that they get from the heads. Yeah. Yeah, so 76% is okay. But initially we have to check from the teacher as well. What that is a metric that they get. Yeah, initially I try to train the teacher as well. And yeah, you can see the student that I get is 76, but the teacher I get is 79. It's just only three difference. Yeah. So this is the things similar to the paper that they said, like yeah, they had 86, but the DistilBERT is 82. Yeah, this is the utility that you can try to implement on that. So you can have a smaller model, but you can get a similarity, almost similarity accuracy that you can get. But this is the idea of this two. Okay, that's it.